The next aspect of the chemistry of wastewater chlorination that we'll consider is the process of dechlorination. Let's start by considering first the motivations for dechlorination. Residual chlorine in water, either in the form of free chlorine or combined chlorine, or perhaps even a combination, expresses toxicity toward aquatic organisms. That's relevant because many measures of water quality are related to the health of fish and other forms of aquatic life. There are several different ways that toxicity of a specific agent can be defined. One of them is called the TL50, or the median tolerance limit. That's the concentration at which half of the population displays mortality, typically in a 96-hour exposure with fish. This is a parameter that can be influenced by temperature in some species. Let's consider first a common fish, the bluegill. Among bluegill, we observe the TL50 to display some temperature dependence, and the typical concentration at which we quantify the TL50 is somewhere between 0.2 and 0.3 of a milligram per liter. Likewise, if we were to consider the channel catfish, another relatively common freshwater fish, we observe that there's no temperature dependence, but the TL50 for this fish is somewhat lower, a little less than 0.1 of a milligram per liter. Now, these concentrations are relevant because they're typically lower than the concentrations of residual chlorine that are discharged or released to the environment from a chlorine-based disinfection process. Next, let's consider where dechlorination is applied. Dechlorination is typically applied as water or immediately upstream of where water is going to be discharged to a surface water source, typically a river, a stream, a lake, or even an ocean. Common applications of dechlorination include chlorinated wastewaters prior to their discharge to the environment, and cooling towers where chlorine is oftentimes applied for biofilm control. If we consider a municipal wastewater application, typically chlorination will be applied in a reactor that has a sort of serpentine geometry as viewed from above, like in the diagram at the right. For this type of reactor, we typically add chlorine at the upstream end of the system and then add a dechlorinating agent at the downstream end of the system, usually immediately prior to its release to the environment. One way of looking at this is that we're applying chlorine and then the dechlorinating agent really to isolate chlorine in only the chlorine contact chamber. In other words, that's the only place that we want chlorine to come into contact with water. Next, let's consider the chemistry of dechlorination, first focusing on how we accomplish elimination of a free chlorine residual. Typically, this is done with a reduced sulfur compound. Historically, this was accomplished by the addition of sulfur dioxide to water. That reaction proceeds to generate sulfurous acid, H2SO3, which in turn dissociates to yield the bisulfite ion, HSO3-. Bisulfite, in turn, will react with free chlorine, here described as HOCl, and if we add those two reactions together, the net result is that sulfur dioxide, a little bit of water, and HOCl yields two strong acids, hydrochloric acid and sulfuric acid. Both of these acids are going to dissociate essentially completely at the pH conditions that characterize most wastewater effluents. Also, if we consider these reactions, their equilibria lie far to the right. So this reaction essentially goes to completion, and it turns out that the forward reaction in this process is extremely fast. Now, as I mentioned, we're going to generate acid as a result of this process. And what that means is that alkalinity will be consumed. Now, SO2 is rarely used anymore because it presents public health hazards and is more difficult to handle than the salt forms, and a common salt form of a dechlorinating agent is sodium bisulfite, NaHSO3. We'll consider next the chemistry involved in dechlorination with combined chlorine. The same reaction is illustrated as before for formation of the bisulfite ion, which in turn will go on to react with monochloramine as a representation of combined chlorine. And we get the net result of those two reactions by just simply adding them up, And again, what we observe is that we generate some acid as a result of this, but also an ammonium ion. Here again, the equilibrium for this reaction lies far to the right, and the forward reaction is fast, but not quite as fast as the reaction that was illustrated for free chlorine. As I mentioned before, acid is going to be produced, which means that alkalinity is going to be consumed, but not quite as much alkalinity consumption as we observe with free chlorine. And then lastly, we notice that ammonia nitrogen is a product of this reaction. Summarizing then, we know that residual chlorine, either in the form of free chlorine or combined chlorine, expresses toxicity toward aquatic life. So there's motivation to get rid of chlorine. The most common way to do that is to apply a dechlorinating agent. Those dechlorinating agents are often applied when treated water is going to be discharged to a surface water. Common applications of dechlorination include municipal wastewater effluents and cooling towers where chlorination is a common process. The stoichiometry of dechlorination based on reduced sulfur compounds is well defined, and the reactions that are involved in this process tend to be very fast. Because of that, process control for dechlorination is based on flow rate through a system, which can be measured in real time and online, and the residual chlorine concentration, which can also be measured in real time and online. As a result, process control for dechlorination can be very effective.